Okay, let's get started. Hello, everyone. So this is Fortin 518 software security. If you want to learn how to be a hacker, especially at the binary level, if you want to exploit binary software vulnerabilities, you are at the right place. My name is Zemin Zhao. I'm a assistant professor in the department. I do all kinds of hacking, mainly at the software level, a little bit at software level. We also do all kinds of defense and other cybersecurity, also work on other kinds of cybersecurity problems. So, some logistics. First of all, I want you to know that we are actually recording all the classes and I will post them on YouTube. So this is the first class of the semester. I hope the IT already set everything up. Looks right on my end. But we will find out later if it is really recording. But I do want you to attend the classes in person because we are going to do some hands-on in class and I will walk around and explain to you how to hack things, and you show me what you did right, what you did wrong, so I can give you feedback there. Also, starting from the next week, I hope everyone can bring a notebook to write down the important things, and also sometimes we will draw the memory, draw the stack for you to better understand how to hack. Also, you should bring your own laptop to the class. We have a hacking platform for this class. You only need a laptop or at least a Chromebook to connect to our cloud server to hack. You don't have to install any specific operating system or tools on your laptop. So everything about this class will be on my website. You just Google my name, you can find my teaching pages, and this will be under this semester's teaching page. So the class is actually almost 3 hours long, just once in a week. So I don't really mind if you want to drink or want to eat something, as long as you can still focus on learning. I'm fine with that. If you have any questions, feel free to interrupt and ask questions. A little bit more about myself. My name is Zemin Zhao. I direct a lab. I call it Cyberspace Security and Forensics Lab, or Cacti Lab. From the name you can tell, we work on all kinds of cybersecurity problems, mainly at the OS and compiler layer, but we do also work on other problems, usable security, network security. I spent almost 10 years in Arizona, so I like Arizona, so I call it Cacti Lab. So in this class, this semester, we do not really have a TA. The department didn't give me a TA. So if you have anything to discuss, you come to me directly. I have an office hour Monday before the class, 3 to 4:30. Or you just shoot me an email. We can meet online, or you can swing by my office. During the office hour, I will also try to join the room link there. So if you cannot make it in person, join the room link. If you want to know more about our research, just visit my website or my lab's website. So all the recordings of the class will go to our YouTube channel here. You can also find the previous classes I taught from computer security to network security. But I mainly teach software security at UB, and also I offer another class, advanced software security at UB. I do not offer that very often because I do not feel we have a big population of security guys yet. So I want to teach this course more, and I actually gave up teaching that course. I want to have more software security guys, then people can take my advanced software security class. A little bit about my lab. like I said, we work on systems and software security. What does that mean? It usually means OS level, compiler level, which means for system security. Some new hardware vendors, they come up with some new hardware features, like Intel. They give a new CPU feature. ARM provide a new CPU feature. We think about how we can utilize those features to secure operating systems and also secure applications. And usually, those new features, how do we interact with CPUs? How do we use those features? You use some instructions. That's the API the CPU provides, right? So, which means we want your program, either OS layer or applications, to have those instructions, to use those instructions. And but most people, they write high-level language programs. They do not directly write assembly. They write a C code, then which means their C code goes through our compiler. After the C code goes through our compiler, we will instrument those new instructions there to make it more secure. So our development usually in the OS layer and compiler layer. We do work on many different architectures. For this course, everything is on the Intel x86 and also the 64-bit Intel. However, for my research, I mainly work on ARM, Cortex-A architecture or Cortex-M. So Cortex-A is, so everyone, your smartphone is based on Cortex-A. So some of you actually are using the new Apple M1 or M2 that is also based on Cortex-A. Most people are still using CPU based on Intel, but some of you are switching to ARM. Then Cortex-M are for those low-end IoT devices. So maybe there are 200 or 300 billion Cortex-M devices out there. So some of them are deeply embedded. They are not directly connected to the internet, so most people do not know. But many of those devices are collecting to internet, like the Nest controller, and in cars, usually there are 20 to 30 Cortex-M devices. So because they are facing to internet now, it's connected to internet, they are also facing all kinds of cybersecurity attacks like our other architectures. We haven't really started to work on RISC-V, but we worked on FPGA a lot, and also we want to work on GPU security because we are in the era of AI. To me, for system guys, it seems we have to work on GPU security. Besides those systems and software topics, we also work on using machine learning, deep learning, or large language models for security, or the security problems with those models. We also work a little bit on autonomous driving security. I co-founded a conference in this area. Also, we work on formally verify security properties of crypto protocols and also code. And in our lab, we do a lot of hacking. We have our own hacking CTF platform. That's what you are going to use for this class. And we also participate in hacking competitions every year. One of the competition we participate every year is called the MITRE Embedded CTF. In that competition, the team of students will design a secure system, quote, secure, then give that system to other teams, and other teams will hack us, and we also hack other teams' designs. So we have been doing that for consecutive 5 years, I believe. We were third place several years ago worldwide, and fourth place last year worldwide. Our worst ranking was ninth place worldwide. So we take that pretty seriously. Do that every year, and that happens in the spring semester. So if some of you, after the semester, you really enjoy this course and you want to learn more about hacking, then I will suggest you to join my team to do that embedded CTF first. I do need students at all levels for funded research, volunteer work, independent study, undergraduate research experience. But for funded research, I only take the very best students, usually from this class. Several of my students, they were master students at UB before, but they took their class, they did very well. Then I recruited them as a PhD student. So in this class, this is actually the first time we offer this class as 518, as a regular graduate level class. The undergraduate level right now, it's 410, but it's going to be 418 soon, maybe next semester. I think it will be approved by the undergraduate curriculum committee soon. So I already invite all of you to join our Slack channel. If you didn't get an email, it's probably in your spam folder. If after checking your spam folder you do not find anything, just shoot me an email. I will add you there. So this class is all about hacking binaries, even though the title is software security. But software, there are many different software. In this class, we focus on binary software. At the end of this class, I hope you will have a good understanding of the theories, principles, techniques, and also tools for binary software and system hacking, and also defense. So in this class, you will get your hands dirty to hack binary software. We do not really cover web software or other high-level languages in this class. Of course, depends on how you define high-level language. Some people will say C, C++, high level, but to me, they directly, the abstraction of that is, I do not call them high-level languages. For example, for Java, Python, you have a garbage collector. For C, you don't have those abstractions. So binary software usually are compiled directly from C or C++. Most people do not write assembly, obviously. You will study in-depth binary, reverse engineering, vulnerability classes, vulnerability analysis, how to write exploit, how to write shellcode, and also you will learn the state-of-art defensive solutions to stop those attacks. You will understand how to crack and protect native software. So I put everything online, the lecture notes, the homework, our hacking platform is also online, the video is online. So even for there will be 2 exams. We call them capture the flag competitions. There are 2 CTFs. They serve as the exams. You are allowed to use anything in those exams. It's open book. You can collect to internet. Probably I don't want you to use ChatGPT or any large language models. The reason is I would not say I have a full understanding of the impact of ChatGPT on my course yet. So for this semester, I'm going to ban ChatGPT just for the CTFs, the exams. In homework, everything, you can still use that. So the key to success in this class is to get your hands dirty. Not only should you understand the principles behind those vulnerabilities, but more importantly, you need to actually exploit those vulnerabilities. And the only way to learn is to hack, to exploit those vulnerabilities. There is no shortcut. So this course is not about memorization of concepts. It's all about understanding, all about problem solving. So I believe that's a better fit for your future environment, no matter you are doing your job or doing research, right? Even in the future, some of you will become a software developer. You will have all the internet available for you. You can use ChatGPT, everything. But you still need to show us you can solve the problem. So it's not about memorizing concepts. So if you really want to be a system or software security guy, I will explain to you where this class lies in the past for you to become a hacker. So some of you took 220 system programming. That class teaches you how to program in a Linux environment. Then there were operating system classes, compiler courses in our undergraduate study. And this class, you need some kind of background knowledge from those courses. But they are not required. I try to keep the class self-contained, especially we have many students who didn't graduate from the UB undergraduate. So in this course, you will learn binary bugs, vulnerabilities, and how to manually exploit them. You are going to use the simplest tools to write those exploits, but they are not automated. After this class, you can take the advanced software security class. Sometimes I offer that one. So that class is about how to automatically discover and exploit the vulnerabilities we study in this class, and also study some advanced defense solutions. So in that class, you are going to develop tools, and those tools will find vulnerabilities. Okay? But without this class, it's not possible to take the other one. So I would say after those classes, then you are probably ready to read and understand some state-of-the-art work in this area. You will be able to understand some papers, know what they're doing, or even say their shortcomings. And become a researcher is actually very easy, as long as you say, there's a state of work and you find a limitation of that work, then you solve that. Then you are doing very good research. So this week, we're going to talk about class overview, logistics, and also I will provide some background knowledge in those areas. We will start with compiler, linker, loader. We'll talk about the Intel architectures, Linux file permissions, what are set UID programs, memory map of a Linux process, what are system calls, what are environment and share variables, and a little bit basic engineering. Probably the last two we will cover next week. So later you will see that why I'm covering this when you see our hacking platform. So like I said, I do not require, there's no prerequisite for this class. I think maybe on the syllabus or on the system at least 220, but I don't really see that as a prerequisite. If you took that, it will definitely help you in this class. But like I said, I try to make this class self-contained. But the real prerequisite for this class is the C programming language. If you struggle in C, you probably will struggle in this class. Because in this class, we are going to read C code, and you will write a little bit C code, not much. There are several assignments you are going to develop some attack tools, but the tools you can use you can write in Python or any Perl or any script language. But you are going to read the C language. So it is a good idea for you to read at least the first half of the C programming language book, the classic C programming language book. Other skills you will learn in this class include reverse engineering. We will use simple tools like obj dump to do that. You can also use more advanced tools like IDA-Pro or Ghidra. IDA-Pro, there is a free version. So IDA-Pro is still the state-of-art disassembler and also decompiler in the market, but it's very expensive. There is a free version, which is enough for our class. Ghidra was developed by a national security agency, and it's free. you can also use that. But actually, I don't want you to rely on those advanced tools in this class. Simple tools like objdump would be good enough. I want you to learn those command lines, how to use that. You also will debug the system, debug the program. We're going to mainly use GDB to do that. The most important skill for you to survive in this class, I would say, is the same skill you use for any research or solving real-world problems. Basically, it's just you need to be good at Googling. When you encounter a problem, you need to know how to formulate that problem, how to find the solutions for that problem, and obviously, Google is the most important skill here. You need to be good at the self-learning, even though I'm here to help you, but hacking, especially binary level hacking, you really need to understand what's going on. Sometimes if one byte is off, then you cannot get the flag. So self-learning is critical here. So the topics we will cover include all kinds of binary attacks and defense. Like I said, we will use the Intel architecture as an example, but most of the vulnerabilities and also exploitation techniques we learn apply to other architectures as well. The platform we are using right now only support x86 and 64-bit of Intel. We are actually developing a new one to support other RISC architectures. We couldn't finish that new platform in the summer, so for this semester, this class, we're still using the old platform. But the new platform is under construction and also it's online. You can play there as well. So here I use the two different terms. One is vulnerability. You need to learn how to discover vulnerability. Another one is exploits. You need to develop exploits. So vulnerability here means a weakness in a software system. And exploit is an attack that leverages that vulnerability to get full control of the system. Some specific topics we will cover include stack-based buffer overflow, how to defend against stack-based buffer overflow attacks, share code development, format string vulnerability, heap-based buffer overflow, or just a heap exploitation, not necessarily buffer overflow, integer overflow, and also return-oriented programming. So usually I will also cover a little bit some attacks at a lower level. So all of these attacks, they are at the instruction set level or software level. Then there are attacks at a lower level, at the microarchitecture level, like cache side channel attack, glitches. Some people call them hardware attacks. Cache side channel are not necessarily hardware. Because at the instruction set level, you cannot directly control the caches, the CPU caches. We probably will spend one class on that as well. We have some, if you go to our platform, you see we do have several experiments for that. So, related books. Obviously, there is no textbook you can strictly follow for this class, but there have been many hacking books out there. Some of them has been 2 decades old, but are still useful. I would suggest this book, Practical Binary Analysis. At least the first several chapters of this book you can read. What we do in this class are the baby steps of hacking. But this Practical Binary Analysis book actually is more like for my advanced software security class. But the first several chapters will give you the background. There are also several papers. I would say I developed this class around. One is SOK paper. SOK means systemization of knowledge. So it's a little bit like a survey paper, but more content than a survey paper. So there was 10 years ago in IEEE Security and Privacy, one of the top security conferences, there was a paper called Eternal War in Memory. So what we're doing in this class are many memory safety problems. So that paper gives a very summary of memory safety problems, and that's what we're doing in this class. Then several years later, there was another book called The State of the Art of the War, Offensive Techniques in Binary Analysis. So that one summarizes, build a taxonomy of how to exploit those software vulnerabilities. There are other papers related, like Shining Light on Shadow Stack, because Shadow Stack is one way to defeat buffer overflows. Those papers can also help. So I will give you those papers throughout the semester for master, at least for master student. I hope you guys can read those papers. So, for example, the first paper, Eternal War in Memory, they gave a figure like this, which is an attack model demonstrating exploit types and policies, mitigating attacks in different stages. They have 6 stages saying how do we use memory vulnerability to hijack a program or fully take control of a system. So right now, obviously, we are going to we will revisit this figure at the end of the semester, and you will see that what we are doing in the semester can map to some of the modules components in this figure. Okay, then the next is our hacking environment. So I will go to a browser. So how do I? So this is our hacking environment. The URL is on the slides. What you need to do is you need to register an account here. So right now, it's not really public. It's you have to access this on UB network. So if you are at home or some other places, you need to VPN into UB campus network. Then you will be able to access this platform. Register account there. Then what you will see many challenges there. So there are probably maybe 100 challenges or something. So those are the challenges I developed for this class, each of them. And I will keep adding new challenges there. So how does it work is, let's say I usually categorize them into, for example, this one is for cache, this one is for heap, there is return-oriented programming, for mastering, and also other categories. Let's go to, let's say, I want you to do a first challenge, I think. It's called, first flag. So you just need to click this challenge. Then there is a run challenge button. Some other buttons doesn't really work. You click the run challenge button. Under the hood, our server will create a container for you. You can SSH in that container, but you don't have to. In our system, where you just click terminal on your browser, it will bring you there directly. That's why I said you do not really need to install anything on your computer for this. So this is a container for you, and if you do a ls there, you can say there are many files in the root file system, and one of them is this program. So this is a program throughout the semester for each container. That's a program you need to hack. And you can see this program has a different color. It's a little bit pink here. That's because this is a set UID program. So I will explain later what this is. And from here, sometimes we give you a code folder. For this one, there is no code folder. In the code folder, we will give you the source code. For some of the challenges, we give you the source code. For some of the challenges, we don't. For example, for the midterm and the final, some of the challenges, I don't want to give you the source code. I want you to hack the binary directly. Then we also installed all kinds of tools here for rob attack, rob gadgets, and also some of our in-house tools you will learn later. So for example, for this one, if you just run this program, then it will give you the flag, okay? So with the flag, you can submit into the system and get 1 point. So the flag is actually in this flag file. So some of you probably have noticed that when you log in here, you log in as the user CTF. You do not log in as a user root. So if you just want to read that flag, you just do a cat flag here. You will not be able to do so because you don't have permissions. Only root can do that, right? Because if you say the flag here, the owner of this file is root, and this is only readable to root. So no other users will be able to get the flag. So if you do a cat here, you will not be able to do that. However, the first flag program is a set UID program, and it will be able to read the file and print the flag for you. After you get the flag, you can just copy this. You copy this flag, you go to the challenge here, then you can, let's see, this one here. Then just submit the flag here. Then you will get the point. So if you just submit anything random, obviously, okay. So for anything else, you just submit some random string, it will not give you the point. So obviously, for each of you, when you log in this system, when you try to solve a challenge, there will be a different flag. So if you submit someone else's flag, we will catch you. Okay, go back to our slides. So like I said, we are actually developing a new platform, which you can also access. We can access here. So this is a new platform we are developing. We already spent several months developing this, but it's not ready for the class yet. The main difference is this platform will support many different architectures, not only x86. So all the challenges will be available for ARM and RISC-V. One challenge is for Cortex-M, those low-end devices. We need to redesign all the challenges because those IoT devices, they do not really have a file system. As you can see, in the previous platform, there is a file system and the flag is in the file system, right? Then there's Linux on top of that. But for those no-end devices, there's no Linux, there's no file system. So we have to embed the flag somewhere in the physical address space. That requires to redesign all the challenges. We haven't done that yet. And also, for the old platform, this one, you only get a terminal. Okay, there is no GUI for you. I think that's enough, actually. For this class, this is enough. But for the new platform, we will have a virtual desktop system. If you register and log in there, you will be able to see. It will be a little bit slower, but for some people who do not have a very strong command line skills, this is a better place to start with. But like I said, we're not using this platform for this semester yet. If you have a strong web development skills, and also you want to learn hacking, maybe you can join my team, help us develop the new system. The hacking environment, I already showed you. We are using x86 and 64-bit Intel architecture. We run the terminal you see there is actually a Ubuntu system. The tools we will use, Pound GDB, Pound tools, and also other GDB plugins we already installed there for you. You can also use NSA Ghidra, or there's another tool called Binary Ninja, which has a cloud version. You just need to register an account. They have a free cloud version for you to use to disassemble binaries. So almost every week this semester, there will be a homework. This semester is weird. We have 16 weeks, but I only have 14 homework. For each homework, I will assign you some readings to do, usually book chapters, white papers, blogs. Of course, there's no way for me to check if you read them or not, but I gave them to you to read for good reason. Then there will be some hacking challenges like what I just showed you. There are several, but most of the challenges I already showed you how to do that in the class. There are others we do not demo in the class, and you need to solve by yourself. So every week you need to submit the homework on UBNearns before the class starts. So before 5 o'clock, you need to submit the homework. 30% penalty if you submit within 10 minutes after class, and 0 point after 10 minutes. Obviously, if I found plagiarism, your homework, at least your homework, you will get 0 points there. Last semester, I taught computer security. I think one guy failed the class because of plagiarism, and more than 6 got other kind of penalty. Yeah. So, well, there are many ways for me to check if you are cheating. Like I said, our system actually have all kinds of mechanisms there to check if you are cheating. So I really want everyone to enjoy this class and learn this, because to me, hacking is really fun. Right? Breaking things is really fun. There is no reason you need to cheat. If you need help, come to me. Also, if you need DA, you need to tell me in the first 2 weeks. Okay, rules for the hacking assignment. So in the homework, for each assignment, you will explain how you exploit that with a simple write-up. Also show a screenshot to show your exploit actually worked. If you worked with other people, you need to tell me who you worked with. So obviously, I encourage you to discuss with each other, but you cannot share your code, you cannot share your exploits or write-ups to the classmates, or you cannot post them online. The exams, like I said, we only have 2 open book exams, and they are all capture the flag competitions, midterm and final. Both of them are 3 hours. So for grades, we have 14 homework, each of them 45 points. So if you do well there, you get 630, so almost pass the course. Then there were the 2 CTFs. After that, I also check attendance every week. We only meet once a week. Obviously, for the first 2 weeks, I just gave the points to everyone. Then there are 2 anonymous class evaluations during the semester, one before midterm, another one before the final. So if 90% of you finish the class evaluation, then everyone gets 10 bonus points. There's no way for me to check who finished that a lot. I can only say the percentage, how many people finish that. So 90% finish that, all of you get bonus points, otherwise 0 bonus points. So for undergraduates and graduates this semester, I use different breakdowns. So undergraduates, you basically get 50 points bonus. You only need to get 874 to get an A, but for graduates, it's 924. The total points you can get in the class is 1K, 1024 there. Academic integrity. So all of you, especially some of them, may be new to UB. So you need to read the computer science and engineering department and also UB AI policies. Also, the first assignment for you in this class is there is a quiz on UB Learns. There are 10 questions. You need to answer them correctly to continue in this class. By answering them correctly, you do not get any point. But if you do not answer them, you cannot continue in the class. This is due in the 2nd week of the class. Go to UB Learns, it's already there. So for the ChatGPT and large language model, I said they are forbidden in the midterm and the final CTF. At least that's a policy now. I need more time to understand their impact on the course. If I feel there's just some positive impact, I may change the policy, but I'm not guaranteeing anything. Also, in this class, you are learning something dangerous. You are learning how to hack software, how to exploit and find vulnerabilities. I call what we do in this class ethical hacking because we have a safe environment which you can hack everything. But do not use what you learn in this class to break laws. If you discover some real-world vulnerabilities using the knowledge you learn from this class, then you should report those vulnerabilities responsibly. And many companies, they actually reward you for doing that. There are cash reward, there are other kind of reward. Okay, I think it's 5:45. Okay, let's maybe talk a little bit about background knowledge, then we can take a break. So the first piece of background knowledge, anyway. Any questions for the logistics, everything? Is this exciting stuff or boring stuff? Cool. Okay. So the first piece of background knowledge I will cover today is compiler, linker, and loader. So let's take a look at how to compile a C program into binary and also run it on operating system and also hardware. So some textbook, like I said, some textbook would say the C programming language is a high-level programming language, but it depends on how you define high-level programming language. To me, C is very flexible. You can basically do anything you want. It provides everything that a low-level language provides. You have all your freedom there. If you program in Java or Python, they are more abstract and you cannot do whatever you want. But still, they have all kinds of vulnerabilities. So, like any other programming language, The source code of that language is human readable. You program in C, you type some that's text, and that's you can read that. Other programs can read that, but computers do not really understand that. Okay, the CPU do not understand your C programming language code. The computer only understands instructions, and those are the APIs CPUs provide to operating system and the programs. So C programming language do not directly run on any machines. So we need a compiler to convert it into a binary code or executable. That binary executable consists of instructions and also data. And those instructions, obviously, they are machine specific. It's the same C code you can compile to run on a RISC machine, RISC-V machine, on an ARM machine, or an Intel machine. And they have different instructions because those machines provide different instruction interfaces. Then your compiler, obviously, are also different. So there are at least 5 phases from a C program to a process running on OS. 4 of them are part of the compiling stage. So we first start with pre-processing, which is this part. Your C program will go through some pre-processing, and the output will be .I program. So it's still text. Then that .I program, so some of you probably use the like pound define, pound if define, those kind of things. So those are C pre-processing directives, right? Those are not really compiled. Those were handled during the pre-processing step. So after that, you have a compiler. For example, we use GCC here. In GCC, the command you use to do the pre-processing is called the CPP. Then if you want to compile that .I program to assembly, then you use GCC -s to do that. Sometimes you also specify what kind of machine you use. Here, if you want to use a 32-bit of Intel, then do M32. Then the output will be the assembly code. But assembly code is still human readable. It's still text. It's not machine code yet. Then the assembly will be handled by a program called assembler to generate the binary code. So each .c program will generate one .o file. We call that object file. That's in our object file, it's already binary. Then several object files, they may be linked together to become one big object file, and we call that one an executable. Then the output of this is one program. It's a file on your file system. It's not a running program yet. So when you really want to run this, the OS has to read this from your storage, usually a file system, hard disk, and load that into memory, then give the control of CPU to that program. So that program becomes a process. So I believe all of you use the GCC to compile C code, but usually what you get is from several C files to the executable directly. You never say what is between, right? So in this class, we are going to see that. Later, I'll show you an example. So for the loader, it will validate if you have the permission to run that program, and the operating system will set up a new process for the program, and also setting up also include setting up the virtual address space for x86, and most modern CPUs we have a hardware module called the Memory Management Unit, MMU. And MMU provides memory virtualization. So each process, they have the illusion that they have their own isolated memory address space. But for some of the low-end IoT devices, there is no MMU. For what we use every day, Cortex-M devices, there's no MMU. So all the applications, tasks running on top of that, they see the full or physical memory address. So the loader or interpreter on Linux is called, we actually use this file, ld-linux.so. This is a library in Linux. So the interpreter or loader is actually in this library. So when you create a new process, both that process and this library will be loaded into memory. Then the OS gives the control to this library first. And this library will load your program, the battery, into the virtual address space. It will process the battery to find out which dynamic memories this battery needs, and also map those dynamic memories into a virtual address space using some system calls. This is the first system call we will talk about in this class. It's called a memory map, mmap. It will map something into the memory space. So it will also do other things, but we can skip this for now. Later, when you see the instructions one by one, it will be much more straightforward. Next, let's see our first concrete example in this class. This is a very simple C program. We have two C files here. One is main.c, another one is add.c. We also have a header file called add.h. Like I said, every C file .c will be compiled into an object file. But the header files, they will not become an object file. They will be expanded in the C file. So in the main function, we can say there are several include directives where include our own header file, add.h, and the three other standard C libraries. Then we have define there. That's define a macro in C program, and that is what the pre-processing will do. Even for those includes, that's pre-processing. So this define will define just a string called usage. Then a string add two integers with 50 and tells you how to use this program. Usage is add A and B, that's it. Then we have the main function. So for most C programs, at least for applications, if you develop C applications, you always have a main function, right? Actually, the main function is not necessary for all C programs. Some of the C programs, they do not really have main functions, like libraries. If you develop library, you don't have a main function. So here we have a main function. This is, from programmer's point of view, this is where your program starts. But obviously before that, the OS, the loader, already did a lot of work. But from programmer's point of view, this is where my program starts. So this program has the main function has two local variables, A and B initialized to 0. Then there is a if statement to check how many arguments are provided here. So for C programs like this, applications, the argument, you see the main function has two arguments. One is argc, which is an integer. That is the number of command line arguments when you invoke this program. Then there is another array of char star. They are basically the command line arguments you gave to the program, each divided by white space or multiple white space. So those arguments, since you develop the main function, when you write a program, you never call the main function, right? You write a lot of functions, you call those functions, but your main function, you never call the main function. Somewhere else call your main function. The C library actually called your main function. So when the C library calls your main function, it will give those parameters to you, the argc and argv to you, to your program. So here we first check how many command line arguments are there. If they are not 3, then we will just print out, then quit. If there are more, if there are exactly 3 arguments, then we are going to change the first argument and second argument. When I say first and the second, there is actually the zeros argument. That's actually the first one. We will change them from ASCII to numbers. That's the C function A to I there, ASCII to integer. Then we just print out, we call the C library function printf. We will print out A plus the number of A, the value of A, plus number of B, plus 50. Then we call another function, and AB. So and AB is another function we define in another file, as you can see in this file. The header file, we only declare, we have a C function, int and this function takes 2 arguments. Both of them are integers. We use if not define those macros. In the C file, we first define base as 50. Then we define the add function there, which just add those A and B and a base, which is 50 here. So this is a very simple C program, and we will use this program to demonstrate what compiler does. So if we go to our platform, you can go to, let's say, and 32. 32 here in our platform right now, 32 means 32-bit, 64 means 64-bit. You run this challenge, then you go to terminal, and if you just run this program without giving any command line arguments, and you see the program print out usage and AB, right? That's because the argument, we didn't give any command line argument. There is only one default command line argument, which is the name of the program. So this one will be treated as the first argument, but we don't have the second and third one. So because of that, the program will go here and print out usage. If we give 2 arguments, like 10 and 20, it will give us 10 plus 20 is 80 because we add 50 there, right? So to compile this program, what you can do is you go to, so in this program, we actually provided the code here. There is a code folder. You can go to the code folder. And we go to that code folder. Then you can see we give you all 3 programs here and also a makefile. If you check the makefile, the makefile is actually what we have here. Is this command. So let me just copy this command. So if you want to compile this program, what you can do is, let me remove this save temps. I don't remember what it is P anyway. Okay. So this is usually how you compile a program. You use GCC, you put all your C files there, you specify this is my output, this is a binary name, and 32 is my binary name, and I want to compile it as a 32-bit program, so hyphen M32. O2 here is optimization level. That really matter for us right now. This WO means give us all the warnings. I'm not sure what is P anymore. Anyway, so you see, when we compile this program, what do we have here? We don't have any intermediate files here. We only have the final binary, right? But if you give GCC other options, you give this -save temps, it will give you all the temp files. It will give you all the temp files we just talked about. For each C file, there will be a .i file, and there will also be a .o file and a .s file. So .i file is the output of the pre-processing. .o is the binary, is the object file. .s is assembly. So we have the .s first, then we have .o, obviously. So let's say for the and .c, you can say the and.c is very small. It's just 5, 6 lines. But if we check and.i, first of all, we will have include.h there, then we have another definition. You can say we do not have those macros anymore. The macros have been expanded here to be something concrete. So this include is replaced by this declaration there, which is in that header file. And this macro base, we don't have that anymore. This is changed to 50, right? So this is pre-processing. Now after pre-processing, we get assembly. And this is what the assembly looks like. In the assembly, this is still text, like I said. There are some labels. There are some assembly instructions, but they are equivalent to machine code, but right now they are readable. They're not really machine code. Then there are other things. Then if we do a .o file, if we can't, you say, it's kind of like we cannot get anything interesting from here. We can have some strings here, but the file itself is not a text file anymore. So we need to use other tools to read this. For example, we can use elfdump to get and.o. Okay, we don't have elfdump here. Then we do a obj dump. Obj dump. Let's do a machine Intel. Oh, I think. D means disassembly. -d here means disassembly. Intel means we want to use the Intel syntax. Then you can see, after this, we get the instructions in this function. So this and function only has 5 instructions. The first instruction is endbr32. That's actually a security feature. We're not talking about that today. Then will be a move instruction, 2 add instructions, then 1 return instruction. So your C code eventually becomes to those 5 instructions here. Okay, I think we can take 10 minutes break. Let's come back 6:15. Yeah. Sounds good? Cool. Okay, let's keep talking about the background. Next, we will study the x86 architecture, which is still the most popular architecture we are using. Most of our servers, most of our desktops are still using this architecture. Obviously, phones are a different story. Our phones are using ARM. Most of the phones are using ARM. So here we first define what are the data types. Usually, a byte obviously is 8 bits. A word usually means 2 bytes, at least for the 32. So for the 32-bit machine, a word means 2 bytes. D word means double word, which is 4 bytes, and Q word is 8 bytes. So if you say those words, you probably need to Google for that architecture, how many bytes it means. Usually that's a number. So then the second concept is endianness. Endianness is the ordering of bytes of a value in the computer memory, storage, or during transmission. So the Intel architecture, ARM architecture, we use the little endian, which means the least significant byte has the lowest address. Let's say we have the address 0, 4 bytes here. We are talking about 4 bytes memory here. Then the address will have 0, 1, 2, 3, right? 4 bytes. Then we have a value, which is, so 0x here means we are using hex. This is a hex value. And the value is 78563412. So if you look at this number, what is the most significant byte here? 78, right? That's 1 byte because it's hex. That is 2 characters, 2 letters here is 1 byte. So 78 is the most significant byte, and 12 is the least significant byte. On a little endian machine like Intel, like ARM, most of the machines we are using right now are little endian. On those machines, which means the least significant byte, which is 12, will go to the lowest address, which means 12 will go to the address 0. 34 will go to the address 1, 56 will go to address 2, and 78 will go to address 3. Okay? So that is what little endian means. In this class, everything will be little endian. However, there are machines are using big endian. For big endian, we store things in the reverse order. So the least significant byte will have the highest address. So 12 will actually go to address 3 instead of going to address 0 there. Okay. So that's the difference between little and big endian. So the x86 architecture, they have 8 32-bit general registers. 1 32-bit flag register called E flags. So E here means extended, right? So before x86, we have older CPUs. We have 16-bit Intel CPUs. And their registers are 16 bits. So they only have the flags register, not the E flags register. Then there is a special register called the instruction pointer register. In this architecture, it's EIP. Every architecture has a register like this. It has the address for the next instruction to be executed. Different architecture have a different name. ARM is called a program counter, PC. And in Intel, it's called pointer register, IP, and it's 32-bit, so it's EIP. And there are many other special registers. So this figure shows the 8 general purpose registers. They are actually easy to remember. They are EAX, EBX, ECX, EDX. Those are 4 of those, A, B, C, D. Then there are 2 pairs. One is ESI, EDI, ESP, and EBP. 2 pairs, ESI, EDI. SI means source index. DI means destination index. SP means stack pointer. BP means base pointer. Then for backward compatible with very old CPUs, those EAX, you can access the least significant 8 bits of it with a register name called AL. So in the very old Intel CPU, 8-bit CPUs, well, I don't remember if they had 8-bit CPUs, but from the very old one, like 80, 86, they have a register called AL. That's 8 bits, 1 byte. Then there is a AH, which is another 8 bits. So AH and AL together, you can use them as AX. That's 16 bits. If you want to use a 32-bit, then will be EAX. And on most of the machines you are using right now, they are 64 bits. So you do not use EAX anymore, you use RAX. RAX is 64 bits. But you can refer to part of it as EAX or AH or AL. So that ABCD, those can be used for all kinds of calculation. And ESI, EDI, you can also use for calculation, but usually they have special meanings. SI, like I said, is a source index. So usually it's used to, if you want to move something from a memory location to another memory location, then you may use SI as the source address, source index, and DI as the destination. And the ESP is for stack pointer, which is very important for this class, but we will go deeper later. So besides those 8 general purpose registers, another very important register is the E-flags register. All other architectures also have this. Sometimes they are not necessarily a standalone register, could be combined with other registers because you don't really have 32 flags here. So for here, what we are interested in are those bits, the carry flag, the parity flag, the 0 flag, and the sign flag. So in this course, you don't really have to remember those flags. But in general, you need to understand why they are there, how they can, what kind of computations are possible because of those flags. Finally, there is instruction pointer, EIP. The value in this register is the address of the next instruction to be executed by the CPU. That's what you need to remember. So for 64-bit Intel machines, we have bigger registers and also more registers. So on the right-hand side, actually, you can say EAX, EBX, ECX, EDX, right? So those are our 32-bit general registers, and they have been extended to bigger registers, to RAX, RBX. Those are 64 bits. Besides that, you can say we have some new registers, R8, R9, R10 to R15. Those registers do not exist in the 32-bit machines. They only exist in the 64-bit machine. Then we have some CR registers. Those are system control registers. Usually, if you program at the application layer, you never touch those registers, but the OS will use those registers. For example, CR0 or CR3 has the page table address. I don't remember which one. Then we have DR registers. Those are debugger registers, also usually used by operating system. We have some segment registers, CS, SS, DS. Those has been there at the very beginning of Intel CPUs. Then we have some other system registers, interrupt descriptor register, IDTR, local descriptor register. Those are also used by the operating system. So in this course, we do not cover them. Then we have some multimedia registers. Usually they are big, 128 bits or even bigger. And you can say some of them can be used partially, like MM0, then XMM0, because for backward compatible. 20 years ago, maybe there is only XMM, so now they have ZMM, which is much bigger. So those are the system registers and general registers for the 32-bit and 64-bit Intel architecture. Next, we will look at some specific instructions. We will use those instructions a lot in the class. You will need to understand what those instructions do. In this class, you are not going to write assembly a lot, a little bit. In the shellcode development module, you will write assembly a little bit, directly using those instructions, but mostly you are going to hack software and don't have to write that. So in the Intel architecture, each instruction is in the form of the blue part there. So it may have a label, then it has a mnemonic, then it has up to 3 operand. So operand are basically arguments at the machine instruction level. The label is optional. You don't need that. You don't have to use that. Then the number of operands for different instructions are different. Some of the instructions do not take any argument. Some can take up to 3. Then each operand or argument here can be a value, just a number. We call that immediate value, which is a number. Also, it can be a register, and it can be also can be a memory address. So each operand is either a source operand or destination operand, or a source operand can be a value, can be a register, can be a memory address. A destination operand, almost the same, but it cannot be an immediate number. So here we have 4 example instructions. The first instruction is called halt. Basically stops the CPU. And from the functionality of this instruction, you can guess. You don't have any argument for it. It's just HALT, halt. It will stop the CPU. Then there is increment instruction. And that increment instruction takes 1 operand, 1 argument. It can be a register. Then it will increment that value in that register by 1. Or it can also be a memory location. Then there could be an add instruction, which take 2 operands, can be 2 registers, EAX, EBX. Then this IMUL is integer multiplication, or this is a signed multiplication actually. Yeah. So this one takes 3 operands. The first operand will be the destination. So the outcome will go to the first register. Then the other 2 are the where we get the values to multiply them together. So this one we probably will just skip this. Later you can look at the slides. I will show you more concrete examples. Okay, so let's look at several concrete examples and understand what those instructions do. Here we have 4 instructions, but actually they are all move instruction. The first one is move, then the square bracket EAX, then comma EBX, right? So what this instruction does is when the CPU executes this instruction, what it does is to move the value in the register EBX to the memory, not to the register, to the memory, to a memory location, and that memory address is in the register EAX. So the square bracket there means that's memory, that's not register. So if we do not have that square bracket, we only have move EAX, comma EBX, then it means we are moving the value in EBX to the register EAX, not to any memory. Okay. So here actually, because it's a 32-bit machine, it implies we are moving 4 bytes because EBX is 4 bytes. Then the next instruction, move EAX, comma, square bracket ESI minus 4. Okay, this one is, we are going to, the CPU will get the value from the memory, and the memory address is ESI minus 4. And get that value and move that value into the register EAX. So the first operand is the destination in this syntax. The third one is move bracket ESI plus EAX times 1, then CL there. So it will move the content in the register CL. So CL is what? CL is part of the register ECX. It's lowest 8 bits, CL. So CL move that 1 byte into the memory. That memory location is at ESI plus EAX times 1, right? So you can say the third instruction, the instruction we just talked about, that's probably very convenient for us to implement array operations, right? The start address of the array will be in the register ESI. The size of each item in the array will be 1. And the index inside that array will be in the register EAX, right? So from that, you can guess what the last instruction does. So the last one, we are moving. So as long as you say the bracket, we are moving something from memory to the register. Okay. So also, sometimes you will say some size directives like a byte pointer, a word pointer. That's because sometimes if you do not use them, it will be ambiguous. We don't know how many bytes we should move. For example, this instruction, move immediate number 2 to this memory location. This actually is ambiguous because the number 2 can be specified just using 1 byte, or it can be specified 2 bytes or 4 bytes. So this instruction doesn't really tell us we are moving 1 byte or 4 bytes. That's why we have this directives. So here, move byte pointer bracket EBX. Then we know that we are moving just only 1 byte, number 2, into this memory location at EBX. Otherwise, if it's D-word, then we are moving 4 bytes. So the move instruction just do data movements. You can move from register to register, memory to register, register to memory, but you cannot do memory to memory directly. The CPU doesn't have an instruction to do that directly from memory to memory. Okay. By the way, move actually also means copy here, because let's say if you move EBX to EAX, you are not changing EBX. So EBX and EAX will have the same value after this move. Then one of the most important instructions in this class is the push instruction. This one, we will spend a lot of time on this. Today I just gave you a brief idea what it does. It will push something onto the stack. And the syntax of this is it only take one argument. It doesn't take more, only one. But where the stack is, this instruction itself doesn't tell you where the instruction is. You do not specify where the stack is. Where the stack is set by the register ESP, stack pointer. So when you push something, let's say you push EAX, what it does is it will first decrement the ESP instruction by 4, because 4 is 32-bit, then place the value of EAX at that memory location. So ESP, the value of ESP is always an address. It's an address in the memory. That's the top of the stack. When you push something, you add something onto the stack, then you first decrement ESP by 4, then place the operand at the where ESP points to. So ESP always points to the top of the stack. However, in this architecture, the stack goes from high address to no address. So when I say the top of the stack, it's actually at a lower address. So if there is push, then there is pop, right? Pop can take one argument or it doesn't take an argument. So when pop doesn't take an argument, then pop will just add 4 to the ESP. If it has an argument, it will pop the top of that stack to a memory or register. So actually, you can use pop to move data from memory to memory. So that's a push and pop instructions. Also, another one is load effective address instruction. This instruction is usually used for quick calculation. Let's say we have this is a complicated instruction. Load effective address, EDI, bracket here, EBX plus 4 times ESI. So what does this instruction do is basically calculate EBX plus 4 times ESI and move that result into EDI. That's it. There are many arithmetic and logic instructions, and subtract, also decrement, integer, multiply, and also shift. So we're not going to go through all the instructions. There are hundreds of them. I do not remember all of them. So when you do disassembly, you say some instruction you don't understand, you just Google and try to learn what it does, okay? Then for control flow instructions, there are jump instructions. It basically change the EIP, the instruction pointer. It transfers program control flow to the instruction at a different memory location indicated by the operand. For example, you can jump to a label at the disassembly label. At an assembly language level, you have labels. You can jump to a label, or after it compiled, it actually jump to it will be a jump to an immediate value, and that immediate value usually is a relative address with the current address. That usually is called a direct jump from program analysis point of view. You can also jump to a register. And that is called an indirect jump. Because when you jump to a register, at the program analysis static time, you don't know the value in that register. Only at runtime, only when you are about to execute this instruction, you will know the value of that register. This is called an indirect jump. Then there are conditional jumps based on some results you calculated before. You decide if you want to jump. So this is like at the C level or other high level language level, you have an if condition, right? So here we have two instructions: compare EBX, EAX. We are going to compare the value of EBX and EAX we find out which one is larger. Then depending on the result, and you can say when we do the compare, the results actually goes to the E-flags register. The E-flags register has the result of this compare. Then this jump less or equal instruction will check the E-flag register and decide what to do. Okay. The compare instruction basically will compare two values, which one is larger, which one is smaller. We will try to go through this really quick so we can see some concrete examples. The call instruction is another very important instruction. This is how you make a function call at the instruction at the machine code level. So this instruction take one operand. It can be a label, it can be a register, it can be a memory location. When it's a memory register, this is called an indirect call, same as the indirect jump we had before. So what this instruction does is it will first push the current code location. The current code location is actually the next instruction's location. What is in the EIP? Push that instruction location onto the current stack. Stack is a memory region in the memory. Push that to stack, then performs unconditional jump to the code location indicated by the operand. Okay. So two operations. First one is push, the next instruction address. The second one is jump. So that's basically what call does. Then return is a reverse operation of call. Return will pop the top of the stack to the instruction pointer. So when you pop that address to the instruction pointer, basically your control flow will go to that address, right? The runtime stack is one of the most important data structure to make our computer runs. It supports procedure calls and also passing of parameters between them. And the stack is located on memory. And for most architectures we are using right now, the stack goes from higher addresses to lower addresses. So when we push a value, the top of the stack, which is pointed by ESP, will decrement. When we pop a value, ESP will increment. So later we will show a demo so you can see that. There are more instructions. I will briefly talk about that, but you don't need to remember them. There is an enter instruction and also leave instruction, and they are equivalent to 3 instructions. We will probably talk about this in 3 weeks. So for the 64-bit machine, like we already saw this figure, you can see the registers gets larger, and we have some new registers we didn't have before. So next, let's say another example. We have another version of the addition code. This one I call it LAND, which is long AND. So let's look at the source code first. This is almost the same as the previous example I showed you. The only difference is previously the 2 local variables A and B, they are int, they are type int, which is 32-bit. Here we change it to long to make sure it's 64-bit for both 64-bit machine and 32-bit machine. So A and B both are 64-bit. So here is a problem, is this piece of code, we're going to run it on 32-bit machine and 64-bit machine. on 32-bit machine, we don't have a register that can hold the value A or value B, right? Because registers are only 32-bit. But the variable we define at the programming language level are 64-bit. So actually we use two registers to hold A or B, okay? So in the program, we print out the size of a lang here, which will be 64-bit or 8 bytes. Then we translate those numbers, we add them together. We just want to add them together. So let's say we want to compile this program to two different machines. One is a 64-bit machine, another one is a 32-bit machine. So this one is 32-bit. Let's try this one first. The program is already compiled here, so we just do a obj dump. Like I said, I use mintel to show us the Intel syntax of disassembly. So this is the Intel syntax. So if we do not use this one, it will show the AT&T syntax. Oops. So this will be AT&T syntax. The register, there is a percentage sign before the register, and the destination will be the second parameter, and the source will be the first parameter. So we don't use this syntax because it's not consistent with other architectures. So for other architectures, we usually only have one syntax. And usually we put the destination as the first operand. So anyway, this is the Intel machine, so we should use the Intel syntax. So for the Intel syntax, we can say, let's say we find the okay. So this is a C program, L and. You can say the function name is L and, right? So after we compile that, this is what we get. Okay, those are the instructions. So go back to this. Here you can say the first argument is an address. The second argument is just an integer. Then we are adding them together. We dereference the first address and add that one. So if we go here, you can say we have 7 instructions after we compile this. We first move ESP. ESP is a stack. We move something from the stack. We move something from the stack to the register EAX. Then EAX will be actually EAX here is also an address. It points to the stack. Then we move what EAX points to EDX. EAX plus 4 points to EDX. Then we move EAX to EAX. So here we are moving two 32-bit value to two 32-bit registers. Then we add them together with another two 32-bit 64-bit value from the stack. So what you can get here is, for a 32-bit machine, we can do 64-bit calculations. We just need more registers to do that and more instructions. Remember, here we have 7 instructions. Okay? If we go to the 64-bit version of the same code, should be somewhere. Here. 64-bit of this, we do an obj dump. You can say we only have 4 instructions, and we are using the registers RAX, RDI. Only those two registers. Okay. You don't have to understand what each instruction is doing right now. We will get there maybe next week. I also want to give you a sense what other architectures look like, even though in this class we're only using Intel architecture, but you can get a feeling what other architecture look like. For ARM architectures, the Cortex-A, like I said, is the one you are using on your new Mac laptops, M1, M2, and also on all of your phones. No matter you are using Android phone, iPhone, or Windows phone, you are using Cortex-A. Cortex-M architectures are for those low-end IoT devices. So for Cortex-A architecture, this is called the RISC architecture. They have many more general registers, you can see. They have 31 general registers. So in the x86, there were 8. In the 64 version, there are more. There are 15, 16. But for Cortex-A, there are 31 general registers. Their names are X0 to X30. Then there are some special registers, like stack pointers. They also call it SP. Then there are program status registers as well. For Cortex-M, since they are for low-end IoT devices, they are much simpler. They only have 16 general registers from R0 to R15. Then there is a program status registers. The stack registers, they actually have 2 stack registers for the kernel level and for the unprivileged level. Just to give you a feeling what other architectures look like. Questions? Okay, so next, let's look at the Linux file permissions. So on Linux, each file or directory has 3 user-based permission groups. One is called owner, another one is called group, and the other one is called others. So owner obviously is the user who owns this file. By default, the person who created the file becomes the owner. You can also change the owner using command chown, change owner. Of course, you have to have the permission to do that. Then the group can contain multiple users, and all users belongs to the group will have the same access permission to the file. Then others applies to everyone else on the file system. Then each file or directory has 3 basic permission types defined for all those 3 user types. They are read, write, and executable. Read means the user or group will have the ability to read this file. Write means they can write, change. Execute means they can run this as a program. Okay. So if you do a ls -l or al on terminal, you will see something like this. So this is a screenshot of my very old laptop, I guess. So at the very left hand, you can see there are how many columns are there? That's 10 columns, right? The first column is either a dash or a D here. So dash here means this is a regular file. As you can see, there are PDF. There are text files. This is a PDF, this is a text file, and there are dash here, means this is a file. Then there are something like this one. It's basically a directory or a folder. Then here it shows it's D, it's a directory, right? Then after that, there are 9 columns. And those 9 columns maps to the permissions for those 3 user groups. The first 3 columns shows the permissions for the owner. So the file's owner is here. I own all those files, and the files group are all here. I am the group and the user and the owner of all of them. So for owners, it's the permission here is read, write, but cannot execute. Because this is not an executable file anyway. This is a PDF, right? Do I have any? No, we don't have. Oh, this one. For this directory, executable means you can go into that directory. Then for the middle three columns means the permissions for the group, for these guys. And the last three columns means the permissions for everyone else. So go back to our system here. Let's see, let's do a ask. So in this system, this is when you log in as CTF, remember? When you log in, you are the user CTF. And you can say, there is one file belong to you, which is r.sh. That file belongs to you. Every other file, they belong to the user root. The flag file, you can say, this is a flag file where you are trying to get the secret, right? This is a capture the flag platform. You are trying to get the secret in the flag. For this file, only the owner can read it. Even the owner cannot write it or execute it. The owner can read it. And the owner is root. Okay? Then for everyone else, they will not be able to do anything, just dash there. That's why right now you log in a CTF and you do a cat flag. You will not have the permission to do so because you belong to here, which you don't have any permission. However, if you get the root privilege, then you will be able to print the value of that. So this one, you can say this one is a little bit special. This one, the last here, it's not showing X. It's not showing executable, right? It's showing S, right? Means this is a set UID program. Okay, cool. We will discuss soon what that is. So this one is link count. Doesn't really matter for this class. This is owner field, group field, file size. Last time it is modified. If you touch it, there's a Linux command called touch. If you touch it, it will update the modified time, and this is a file name. So for set UID programs, basically, let's skip this part. So each Linux and the Unix process, they have three UIDs associated with it, user IDs associated with it. The first one is called real UID. Well, thank you for doing that. Oh, very nice guy. So each Linux and Unix process has three user IDs associated with it. The first one is called the real UID. So this is the UID of the user or process that created this process. Then there is something called effective UID. So this is the UID used to evaluate the OS. We'll use this UID to evaluate the permission and the privilege of the process. Then there is a safety UID, which is not super important for now. So this is a feature in Linux and Unix operating systems. Windows doesn't really have this. Mac obviously is similar to Unix, so they have this, but Windows doesn't have this. So the OS, the kernel, makes the decision whether a process has the privilege or permission to do something based on the effective user ID, EUID, not the real user ID. So for most programs, the effective user ID is the owner of the program, or the effective user ID will be the same as the real user ID. However, if you set a program as a set UID program, then that program, when it runs, its effective UID will not be its real user ID. Instead, it will be the owner of that program. That's why, let's say, go back here. So all our challenges, they are set UID programs because this bit is S instead of X. It means this is a set UID program. So when I run this program as a CTF, so if it's a regular program, when I run a regular program as a user CTF, then that process will have the effective user ID of whoever is running it. In this case, we're CTF. However, when I type this, when I type this here, whatever. When I type this, when I execute this, when I execute the program, I'm CTF. But because this program is a set UID program, it actually has a permission of the owner of the program, and the owner of the program is root, not CTF. So even though I can run this program, the program has higher privilege than me. So this is a feature of Linux, and our CTF platform is designed around this idea, right? That you can say the flag of the CTF user you cannot get. However, if you run this program and you can exploit the vulnerability of this program, you will be root and you will be able to read this flag. Okay. There are many set UID programs in the Linux system. For example, SU switch user, sudo, and also something need a root privilege like unmount. Also interesting stories. Do you guys know that sudo was developed at UB? Some of you know, yeah, good. Yeah. So you can see all those set UID programs, they have this bit S here instead of X. Make them the set UID program. Let's look at one more example. This is a read secret program. The main function here, we have a local buffer, 100 bytes. Then we make the system call here, get UID. That's a C library function, but that C library function eventually makes a system call. System call goes to the Linux kernel, and the kernel returns a value. So here we get the UID that will be the real ID of the process. Then we get the EU ID. We make another call here. Get EU ID to get the effective user ID of the program. Then we print out the user's name. Then we just print the flag. The print flag function will just open the flag file and print the content. So what do you expect to see if we run this program on our server? The first time it print out the UID. What should it print out? So here it will print out UID. It will be whoever runs that. So we are running this as user CTF. It will print out the username CTF. Second time, it will get EUID. Because this is a set UID program, the EUID is the owner. So here it will print out root. Then it will print out the flag here, right? So if we go to the server, read the secret, yeah. So when we run this program, you can see the UI, when we run this process, the UID of this process is whoever runs this program, which is CTF in this case. And the UID here is 1000 because Linux reserve anything smaller than 1000 for kernel use. So as the first user on the system, we have the number 1000 CTF. Then the EUID of this process is actually root. That's why the program and the EUID is what the OS use to evaluate the program's permission. That's why the program can read the flag and print it out. Okay, then we talk a little bit about the ELF files. This is a huge topic, so I don't want to talk too much about it because we can take a whole semester talking about this. We just need to learn what we need for this class. So the full name for ELF files are executable and linkable format. So this is the standard file for executables used by many OSs like Linux. In Linux systems, the extension doesn't really matter. On Windows, you have all kinds of extensions, and those extensions matter, right? There's .exe for executable, PDF for PDF. For Linux, the extension doesn't really matter. Usually, we have many different extensions. But they are just for information. We have many different extensions for ELF files. For example, we have bin, .bin, usually means this is a binary. We should .elf, .o, we already saw .o today. That's an object file. And also .ko means a kernel object. Usually it's a loadable kernel object. And also mod, I think mod is also a module. So means a static object, usually a library. And also for some embedded system, you will find AFX and other extensions. So an ELF file contains the program and data, and it also describes how a program should be loaded. Contains the metadata describing the program contents. So in Linux, we can use the file command to tell you what file this is. For example, we use ls multiple times today. ls is an executable, right? It lists the files in the current folder. But for that executable itself, we can use the command file to tell what it is. For example, on my machine, I do a file /bin/ls, and it tells me this is a ELF file, 64-bit. It runs on x86 34-bit machine. It is dynamically linked. Its interpreter is that one, which I showed you before. That's an interpreter, which means the OS will load that interpreter. That interpreter will load this program into memory. It's hash value, and it's stripped, means it doesn't have those symbol values, symbols anymore. And we also have other tools like readelf to show you different segments in this ELF file. So we do elf. We can say that's a header. This one was compiled for Linux system, and it's a dynamic dyn dynamic linked system, and it has so many sections. The sections has names like interpreter, load, dynamic symbols, init, PLT. Those are different section names. So some important sections are .text. This is where the code, the instructions are, .text. Then there is PLT or GOT. So they are used for dynamic libraries. Then .data section is usually for pre-initialized global data, like a global variable. Usually we'll go to .data section. Then some of the data is supposed to be read-only. Then they go to read-only data section, RO data. Also, there is another section called BSS. I don't remember what BSS stands for, but this is a section for uninitialized global data. Okay, for example, if you have a C code, there are global variable int A, int B, and you never initialize them. So, any C program here, can you tell me if you do not initialize a global variable, what should be its default value? Yes, that's right. It will not be, in C standard, it will not be any random value. It should be 0. So the BSS section has all of those uninitialized data. So in your L file, which is a file, after compile in your file system, you will load that code and data from that file to your memory. So when you load that, there is one section you don't really need to load. The .text, that's an instruction, you will load them. .data, that's initialized global variables, you will load them. Read-only data, you load them. But BSS section, you don't really need to load anything from the L file. Because according to C standard, their value should be 0, right? So there are many tools for us to work on L files. You use GCC or other compilers. You will generate an L file. Use readelf to pass the header. In this class, we are going to use obj dump a lot to get a disassembly from an L file. You already saw that multiple times today. We use nm to see the symbols in the L file. Let's say here, this is a program. We use nm to list the symbols in the program. Right? It's a very short program, but there are so many symbols there. Some of the symbols are not introduced by developers like us. They were part of the standard C library. Let's say, what do we have there? For example, main, that's what we introduced. Print flag, that's what we introduced. And they are in T section, means they are text, they are code. There are also some variables. Do we define any global variable? Maybe not. Anyway, so that's another tool. The patch elf, we can use it to change L files. obj dump, we are going to use this tool when we develop shellcode. This is a tool to copy specific elf sections or carve specific elf sections. Also, we have a strip to remove symbols. Let's see, that could be fun. Let's see. We need to move this to temp, I guess. No, we don't have permission to do that. Okay. Then there are libraries for you to analyze L files as well. So those are tools for L files. Okay, memory map of a Linux process. So each process in a multitasking OS have the illusion that it has its own memory, full memory. For a 32-bit machine, which means every program believes it has 32-bit memory address, which is 4 GB, okay? So more than 4 billion bytes. However, obviously, our physical computer may not have 4 GB or memory, right? For 20 years ago, most computers only have like 256 megabytes, but each process, they believe they have 4 GB. That's because they have this virtual memory illusion created by MMU. Then those virtual memory addresses, they are mapped to physical memory addresses through something called page tables. And MMU, which is a hardware, which is part of the CPU, will walk through the page tables to translate virtual addresses into physical addresses. And for this figure, this map is a little bit obsolete, but still consistent with what we are using nowadays. In general, it's consistent. So this is a memory map of a 32-bit Linux process. At the very top, we reserve 1 GB for the kernel. Then for at the bottom, that's where we first put our code. For one application becomes a process, we put its own code at the very low end, not at the 0. Okay, you cannot put at the address 0, because for C programs, 0 means something special, right? 0 means null, means invalid, right? So we do not use 0. Then we have the data segments, which is dot data. Whatever in dot data in the elf, we copy there. Then we have BSS segment, which is uninitialized variables. Then after that, we have the heap. Then after that, we have the libraries. The libraries for C programs, we always have the C library, libc. We also may have other libraries, like the interpreter, the loader. Those are memory mapped to the address higher than heap, usually. Then we have a stack, which had a very high locate address, and they go down, okay? If it's a multi-thread program, then obviously each thread has their own stack. So that's a general memory map of a 32-bit program. And we know that in C, we define a non-pointer, which is 0. And probably, I don't know, any of you thought about how this is implemented. Why 0 is so special? 0 should not be special. 0 is special because whoever come up with this idea, I don't know who come up with this idea, probably the guy who developed Linux. They want to define 0 as special. But for physical memory, think about physical memory. If you have a 4 GB physical memory, then 0 at a physical address, that's a valid address, right? Your memory is 4 GB physically. Then it has the address 0 to 4 GB. So 0 is valid. So we actually define zeros as invalid through this MMU thing. So basically, we map the virtual address 0 to a place that doesn't exist. Okay, so that is how it is. That is what we do. That's why at the beginning of here, we do not map anything. Okay. Then the next step is to look at a real memory map of a function. I think I have 2 functions here. I have 2 programs here for you to use. The program is very simple. It doesn't do anything. It's a main function and a get char. It will basically wait for you to input a character, then it returns. So if you do not input a character, it will stay there, right? So then give us the opportunity to look at its memory. 2 versions of this program on our server, 32-bit and 64-bit. Where's the 32-bit? Okay, so process map 32. This is 32-bit of the program. We run this. So this is where you probably want to have multiple terminals. So we installed the tmux on this system. So you type tmux, then you do Control B, semicolon there. Oops. What I'm doing. Control B double quotes there. Then you split it into 2 terminals. So this one, let's run this program. Okay, now this program is running. It awaits me for a character. I'm not giving it a character, so it will not quit. Then in another terminal, I'm trying to print its map. How do we do that? We first get the PID of this. So in Linux, we get a PID. We can do PS AUX. We get all the process running in the system. There are Oh, then actually not many. Here, right? So this is this program. So say the PID is 60. Then we use a command. We can use a command cap proc. So in the proc file system, it has its map. Proc, then PID 60. Then maps. Maps. Okay. So now we see the map of this program. Let's say. Oops. Somehow I cannot move that. Anyway. So from here you can see a little bit, right? The stack is at a very high. So this is a. Let me just remove this for me. Okay, this way. So now we can see the full map of this program. This is relatively lower address, and here we have the program itself. Those are the text.data.bss modules of this program. Then we have the heap here. Then after the heap, what do we have? We have the C library. After the C library, here we have the interpreter library. Then at a relatively higher address, it has a stack. Okay, it's not strictly the same as what we have here in terms of the address. Here you say the address is quite small. Here we are at the maybe 1 GB break of the memory, but the order is almost the same, right? So here we have the program itself, including data section, code sections. We have the heap. We have shared libraries, which have the stack. Here almost the same, right? Program, heap, shared library, and stack, right? So that's a 32-bit. If we look at the 64-bit, we find it has the same PID actually. So we do a cat 60 maps. Let's get rid of this one. You can see for the 64-bit, the first thing you'll notice is the address is much longer because the address is supposed to be 34 bits. Of course, the architecture we're using right now, we're not really using the full 64 bits. We're using something around the 69 bits, if I remember correctly. But you can see it's much longer than before, right? Then almost the same order. There's a program first, heap, shared libraries, and also stack. Right? So that's the memory map of the Linux program. Oh, I guess that's it. Okay, cool. So, any questions? That's probably a lot to digest. There will be a little bit more background we will cover. No, we don't have a class next week, right? We're coming back in 2 weeks. There will be a little bit more background to cover. Then we're just diving into hacking directly. And I do not expect you to understand all the background right away. And I hope you can pick up the background when you hack, right? When you hack, you realize, oh, this is a part I don't understand, so I need to go back to the background. That's usually how we learn. So treat this class more like challenge-oriented. There are 100 challenges, and your goal is to solve them. And to solve those challenges, you need to Google. You need to pick up some background together by yourself. And like I said, I try to make the class self-contained. Okay. Any questions? So that's called the SetUID program. Actually, I will give you some materials to read. Read those first. Yeah. Okay. Okay. So we are not meeting next week. I think there's a typo. I think the homework 1 is due before the class of is before Labor Day. Even though we do not meet, but we have a due there. If that's a typo, I will correct that and I will send you guys email. And also, what else? I mainly use Slack to communicate with you. So usually, if you have any questions, you ping me on Slack. I try to answer right away. And I want to use Slack because everyone else can also say your question, and maybe that question will address their concerns as well. You need to finish the AI quiz by next week. Maybe I can give you a little bit of extension, but it's already on UB Nerds. Okay, cool. See you in 2 weeks, I guess.